Hello, I'm Professor Afshar at Glendale Community College. This is Physics 101, Lecture 45. In this lecture, we'll discuss angular momentum. This topic is covered in Chapter 11 of our textbook by Surway and Jewett. I want to start this lecture by reminding you of the conserved quantities that we have learned about. So far in this semester, we've learned about two conserved quantities, energy and momentum. These two are extremely important because they help us find unknown quantities. They give us predictive power in some sense. We live in a universe where everything is changing all the time, and so it's rare to find quantities that are conserved, that stay constant from 1 second to the next. Energy and momentum are two examples. Today you will see a third example of a conserved quantity. Remember why energy and momentum are important. They are essentially important because under the right conditions, they can help us figure out things that we would not otherwise know. For example, knowing the work done by non-conservative forces tells us how energy must change, so we can figure out the change in the energy of the system if we know the work that is being done by friction, for example. And in certain cases, if drag or friction or other non-conservative forces can be ignored, then we can even say that the final energy of a system is going to be equal to the initial energy of the system. This equation is important because once we flesh it out, we will see that we can use it to calculate the speed or maybe the extension of a spring or maybe the height of an object that is falling using this formula. So this formula gives us a certain measure of predictive power. Similarly, with momentum, knowing the sum of external forces tells us how momentum must change. Remember, this was the relationship between the rate of change in momentum and forces. If we know what forces are acting on a system and we can add them together, then we know how the momentum is going to change. If the external forces are absent or if they just add up to zero, then dp dt is going to be equal to zero, which basically tells us momentum is constant. So P final is equal to P initial. Again, this equation gives us predictive power. If we can figure out the initial momentum of the system, we can then figure out its final momentum. And from that, we can calculate things like the final velocity of an object. In this lecture, I'll introduce you to a third quantity that, like momentum and energy, is conserved and therefore is equally useful. This new quantity is called angular momentum. Before defining angular momentum precisely, let's consider the torque that acts on a point particle. Specifically, let's consider a point particle in uniform circular motion. Remember, uniform circular motion was circular motion with a constant speed. Now, if we want to calculate the net torque on this point particle, we need the net force. Remember, in general, the torque of any force is simply equal to the position of that force cross the force. If here we're interested in the net torque, then we should have the net force in this formula. Of course, according to Mr. Newton and his second law of motion, the net force on a system is equal to the mass of the system times the acceleration of that system. So I can replace F net with ma in this context. Now recall that we're talking about uniform circular motion, and for uniform circular motion, the acceleration vector points along the radial direction. More specifically, it points inwards directly to the center. In that case, the r vector and the a vector are said to be collinear. They are said to point along the same line. The position vector points from the center to the circumference, whereas the acceleration vector basically points from the circumference to the center. So they are both collinear, or they are simply parallel to one another. This fact is important because it means that their cross product is going to be zero. Remember how we calculate the cross product of two vectors? We take the magnitude of the first vector multiplied by the magnitude of the second vector, and then we multiply by the sine of the angle between those two vectors. In this case, what I'm saying is that the angle between R and A is 180 degrees, and sine of 180 degrees is 0. So here I'm telling you that for a point particle in uniform circular motion, the net torque must be equal to 0. Now, save that fact for a minute. Let's do this calculation in a slightly different way. Once again, I can say net torque is simply R cross F net. Then I can remember that the net force is equal to the rate of change in linear momentum with respect to time. This is a fact that should make sense to you. After all, momentum is just mass times velocity. Mass is a constant, so the derivative of momentum is simply mass times the derivative of v with respect to t. And of course, the derivative of v with respect to t is just acceleration. So yes, it makes sense that dp dt is equal to mass times acceleration, which is equal to F net. Now here's a very tricky step. It turns out R cross dp dt is equal to this quantity here. Now this is at first kind of strange, just thinking about it purely mathematically. When you compare this second line to this third line, you should be concluding that v cross p is 0. And it is. Remember that p, momentum, is simply mass times velocity. When you take the velocity vector and you multiply it by the mass of the object, you make that velocity vector longer or shorter, but you don't change its orientation, which means that v and p are parallel, which means the angle between them is 0 degrees. Of course, when you take the cross product of two vectors, you need to multiply the magnitude of the first vector times the magnitude of the second vector times sine of the angle between them. Sine of 0 degrees is 0. So this quantity here, v cross p, is simply 0, and I am free to add 0 to this equation and still maintain the equality. Now this looks like a very strange thing to do. You might be wondering, why am I adding 0 to this quantity and making it look a lot more complicated? The reason I'm doing that is because I can write v as dr dt. That's what velocity is. And if you look at this expression, this should remind you of something that you saw maybe a while back in your calculus class. It was called the product rule. Remember how the derivative of a product obeys a very specific rule? Notice how we have r cross the derivative of p plus the derivative of r cross p. This expression here can be written as the derivative of r cross p, right? If you have the product of two functions and you want to take the derivative of the product, you take the derivative of one times the other one, and then you add the derivative of the other one times the first one. So this whole mess here can be written as the derivative of r cross p. Now you might be thinking that I've taken something very simple and made it extremely complicated. After all, on the left side, we found that the net torque is 0, but here on the right side, through this very tricky set of manipulations, I have found that the net torque can also be written as the derivative of r cross p. Now think about this for a second. What we have essentially shown is that this quantity here must equal to this quantity here. And think about what that means. We're saying that there is a quantity r cross p, and the derivative of that quantity is equal to 0. So we're in effect saying that that quantity does not change. We're in effect saying that this particular combination of position and momentum is something that is constant. So we've discovered a conserved quantity. This conserved quantity is referred to as angular momentum. It is denoted using the letter L. We put an arrow on it to remind ourselves that it's a vector, so it has x and y and z components. and L is defined as R cross P. So on the previous slide, we examined the motion of a point particle, and we found that there is a special quantity that is conserved. We termed that quantity angular momentum, and we found that for a point particle, the angular momentum is R cross P. The question now is, what is the angular momentum of an extended body? In other words, if you have an object, a large object that consists of many particles or many atoms, how do we figure out this conserved angular momentum quantity for this extended body? Well, to find the angular momentum for the entire system or for the extended body, we simply add the angular momentums of the individual particles. So as we've done in the past, we're going to look at every atom of the object. We're going to label them atom 1, atom 2, atom 3, and in general, we'll use the index n to label these atoms. And then we'll calculate the angular momentum for each individual atom. Remember, angular momentum is R cross P. So we're going to take the position of the nth atom and multiply it by the linear momentum of the nth atom, and that gives us the angular momentum of the nth atom. And then we'll just add those together for all the atoms, and that gives us the total angular momentum. Now remember that linear momentum is mass times velocity, so I can just write P sub n as m times v sub n. And of course, I can move the m outside of the cross product. The cross product is really a vector operation. You can write this m wherever you please. Now I'm going to do something kind of strange. I'm going to write this quantity as follows. So m and the rest of this quantity are left intact. It's just that I'm multiplying by r squared and I'm dividing by r squared. The reason I'm doing this is because it turns out this entire fraction is simply equal to omega. So r cross v divided by r squared is equal to omega. This is not an expression that we have proven, and proving it would require a lengthy tangent, but it should seem plausible to you because after all, you know that there is a relationship between the linear quantities and the angular quantities. Specifically, we have mentioned how the linear speed is equal to r times the angular speed. So if you rearrange this equation, you can see that omega is equal to v over r, and you might even want to write it as something like rv over r squared, and then you begin to notice that this expression here looks a lot like this expression here. The point here is, the important point is that I can write angular momentum in terms of angular velocity. And of course, this expression here, mr squared, should look very familiar to you. If you remember, we defined the moment of inertia of an object as mr squared. More precisely, if you have an extended body and you want to know how quote-unquote difficult it is to rotate, you have to calculate its moment of inertia. And to do that, you would need the mass of its particles and the position of each particle. And when you take that position and you square it and you multiply it by mass and you add it for all the particles of that object, you get the moment of inertia. So the angular momentum of an extended body, a large rigid object with many particles, is equal to the inertia of that object times the angular velocity of that object. So we now have two expressions for angular momentum. Angular momentum is a conserved quantity, but to calculate it, you have to decide whether you're talking about a point particle or an extended body. If you want to figure out the angular momentum of just a single atom or a point particle, you use this equation here, r cross p. But if you have a larger object and it's not really practical to add trillions and trillions of angular momentums together, then you use this second expression. For an extended body, the angular momentum is equal to I, which is the moment of inertia, times the angular velocity. Now you might be wondering why we care about angular momentum. Why is it important? Well, it's important basically for the same reason that energy and linear momentum were important. It's a useful quantity in solving practical problems. But a little more technically, the real reason is the principle of angular momentum conservation, which states that in the absence of external interactions, the total angular momentum of a system is constant in time. So this is precisely what we mean by conservation of angular momentum. It's a quantity that is constant in time. Notice that the principle does say that this is true in the absence of external interactions. This phrase in this context means that the net external torque is zero. Recall that we also encountered the principle of linear momentum conservation, and in that context, back in chapter 9, we saw this phrase there as well, absence of external interactions. There, in the context of linear momentum, absence of external interactions meant that the net external force was equal to zero, but in the context of angular momentum, it's the net external torque that must be zero in order for the angular momentum to be conserved. This principle is quite important, and so you're going to see it written down in many different ways. Here's one way to say the same thing. If the sum of the external torques is equal to zero, then L initial is equal to L final. Remember, we're using the letter L for angular momentum, and when we say that it is constant or conserved, we're basically saying the initial is equal to a final. Sometimes we'll also say the same thing by saying that delta L is equal to zero. Of course, it's the same thing because delta L is L final minus L initial. And a slightly more mathematically sophisticated way of saying the same thing is to say that the derivative of angular momentum with respect to time is equal to zero. You should be comfortable with conservation of angular momentum written in any of these forms. Each one of these equations provides a useful equation that you could potentially solve to find information about the final state of the system. So the principle of angular momentum conservation states that in the absence of external interactions, when the sum of the external torques is equal to zero, angular momentum is conserved. So you might be wondering, well, what happens if the net external torque is not zero? In that case, we use this equation here. It turns out this is an important relationship between angular momentum and the net torque. This expression tells us how angular momentum changes when there are external torques acting on the system. To prove this fact, we'd have to prove it once for a single particle and then again for an extended body, simply because we now have two different formulas, one for a single particle and one for an extended body. The derivative of the angular momentum of a point particle is simply equal to the derivative of r cross p. We can apply the product rule to the product of r and p, which means we'll take the derivative of the first item in the product and then multiply it by p, and then we'll add to that the first item in the product times the derivative of the second item. Remember that when you take the derivative of r with respect to t, you simply get velocity. And then also remember that velocity and momentum point in the same direction, because after all, momentum is mass times velocity. When you take the velocity vector and you multiply it by, let's say, a number like 3, you're making it 3 times longer, but you're not reorienting it, you're not changing its direction. Since v and p point in the same direction, the angle between them is 0, so sine of 0 is 0, and therefore v cross p is equal to 0, which means this whole mess simplifies to r cross dp dt. Then you might remember that dp dt is simply f net. And of course, when we say f net, we mean the sum of the external forces and the internal forces. The internal forces cancel each other out thanks to Newton's third law of motion. Every time one component, let's say A, pushes on another component, let's say B, B pushes back on component A, and those two forces cancel. So what we're left with are the external forces, R cross F external. And of course, this is exactly what we mean by torque. This is torque is R cross F, but of course, if we're talking about external forces, then we're going to be talking about external torques. We can also prove this result for an extended body. Remember that the angular momentum of an extended body is I omega. I, like the mass of the body, is constant, so you can bring it out of the derivative. You're now left with the derivative of omega, and of course, remember the derivative of angular velocity is simply angular acceleration. And then we remember the connection between torque and angular acceleration. I alpha, thanks to the angular version of Newton's second law of motion, is simply the net external torque. So whether you're talking about a single particle or an extended body, there's a nice connection between angular momentum and torque. We did not prove the principle of angular momentum conservation, but now that we have this expression, you can see where it comes from. If the right side of this equation is equal to 0, that's tantamount to saying absence of external interactions, then dl dt is going to be equal to 0, which means L is not changing, which means L initial is equal to L final. So the principle of angular momentum conservation can be derived from this important relationship here. Let's end this lecture with a practice problem. Consider a disk with moment of inertia I1 rotating about a vertical axis with angular velocity omega initial. A second disk with moment of inertia I2 initially at rest is dropped onto the first disk. Because of friction between the two disks, the two eventually reach the same angular velocity omega final. Find the final angular velocity omega sub f. So in some sense, what we're talking about is a collision problem, but not collision in the sense of chapter 9. There we were talking about the linear motion of particles that would meet either in a head-on or a glancing collision. Here we're essentially talking about the collision of two spinning objects. We have one disk here and its moment of inertia is I1. In theory, we could look up the moment of inertia of a disk and maybe even find a numerical value for it. But in this particular problem, I want to do everything in terms of variables. So disk 1 has moment of inertia I1 and it is rotating with some angular speed, which we're just going to call omega sub I, the initial angular speed. You can pretend like that's given to you. Now there is a second disk, and both disks, notice, have the same axis of rotation, although initially the second disk is not rotating. We're going to drop this second disk, so we're going to let it slide down the axle and make contact with the first disk. So in a sense, this is a collision between disk 2 and disk 1. There's a certain amount of friction between these, which means when disk 2 makes contact with disk 1 is going to force the second disk to rotate. More precisely, what happens is that disk 1 slows down and disk 2 speeds up, and after a few seconds, both disks will be rotating together at some intermediate speed. We want to know what that final intermediate speed of the two disk system is going to be. Recall from chapter 9 that we used conservation of linear momentum to deal with linear collision problems, so it shouldn't be any surprise that in this case we're going to use conservation of angular momentum because we're essentially talking about an angular collision problem. So we're going to say that L initial is equal to L final. This is conservation of angular momentum. Of course, when I say L, in this case, I mean I omega. We are not talking about point particles. We're talking about extended bodies or rigid objects. For an extended body, we use the formula I omega. L initial is simply the angular momentum of disk 1. Remember, disk 2 initially is not rotating, so its angular velocity is 0. So we only need to worry about the first disk initially. That's going to be I1 times omega initial. Finally, both disks are rotating, so I need to know the moment of inertia of the entire system. That's simply I1 plus I2. And then, of course, the system is rotating with angular velocity omega final. I don't know what that is, but I can now solve for it. And omega final turns out to be I1 over the net moment of inertia times whatever the initial angular speed was. Part B of the same problem says find the initial and final kinetic energies of the system. Notice that we are talking about objects that are executing pure rotational motion, so we should be talking about angular kinetic energy here. Initially, it's only disk 1 that is rotating. Disk 2 has no kinetic energy, so we can say K initial is 1/2 I omega squared, except the I is going to be I of object 1 because that's the only thing that's rotating, and omega, of course, is the initial angular speed. Finally, both objects are rotating together. I can use the formula 1/2 I omega squared again, but now I is going to have to be the total inertia of the system, I1 plus I2, because both disks are rotating. And omega, of course, is the final angular speed. I have figured that out in part A. So I can now take this expression here and substitute it for omega final here, remembering to square it. And after a little bit of algebra, we find that the final kinetic energy of the system is 1/2 I1 squared over I1 plus I2 times omega initial squared. And that's the end of this lecture. Thank you for your attention.